So hopefully we have a good model, a frame of reference on the subatomic particles that make up the atom and how they relate to one another. Now we need to learn how to count the different subatomic particles. And so this section is going to talk about isotopes, and then the next one is ions. So as atoms are generally too small to be measured individually in experiments, it is important to know how to analyze atoms quantitatively. Remember quantity, so you've got a number, by knowing fundamental properties of the atoms of each element. You can use these properties to count the number of atoms in an element in a sample with a known mass. So a long time ago they were able to get the mass of different things and deduce from there what was making up those atoms. So atoms of different elements, by the way, I ordered a new pen today. Hopefully it will maybe write a little bit better than this one. Of different elements have different numbers of protons. Therefore, atoms of the same element have the same number of protons. So the atomic number, which can be symbolized with a capital italicized Z, okay, of an element, is the number of protons of each atom of that element. And it identifies an element. Okay, so the atomic number, again, that's a capital italicized Z, can usually be found above an element symbol on the periodic table, although some periodic tables have this reversed. In fact, the ones that are up on our front table that we got from the Army Reserve actually have this reversed. So how do you know which one is the atomic number? Let me see if I can find a different colored pen here. So it will be a whole number, that's important, and it will increase by 1 for each element, whereas the other number will increase by more than 1 and usually go to the tens or hundreds place. Okay, regardless, elements are arranged in the periodic table in increasing atomic number. Super important that you go on and understand that if you did not already know that. So I've got silver, which actually has the element symbol Ag. Not at all like silver, but that's what it is on the periodic table, Ag. And it has the number 47 on the top of our one on the wall. And then it's got 107.9. So if you're looking at that and using the rules that I was just talking about, you would know that this top one right here is the atomic number because it is a whole number. Okay, it's a whole number, no decimal points. And if you look at the ones to the left and right of silver, you'll notice that we have lead, which is the number 46 on top. And then we have cadmium, which has the number 48. And so you just have to learn which number it is that you're looking for. Most of the time they're on the top, but again, sometimes they're on the bottom. And on our ones that are laminated, that would actually be written just the other way. Now, another important thing to understand is that all elements are neutral. And so if it has 47 protons, which are positive, then it also has to have 47 electrons because your positive and negative have to cancel each other out. Now, even though our protons have to stay the same, our neutrons can vary. And when they do, they have a special term. They're called isotopes. So many naturally occurring elements have elemental forms with different numbers of neutrons and are called isotopes. So most elements consist of mixtures of isotopes. You'll be working on an activity called the atomic mass of candium, where you will learn a little bit more how this works. But that atomic mass that's at the bottom Remember we had silver, and I think it was like 107-ish, something like that. This mass is actually a mixture, or an average, excuse me, of all of the isotopes of silver that occur in nature. So this number is not just the mass of one isotope, but of many, and that will be important for you to know later on. So isotopes are atoms of the same element that have different masses, and thus they have a different number of neutrons. Now remember, the protons have to stay the same or else you've got a different element, but the neutrons can change. And when they are different, the mass of course changes because mass equals protons plus neutrons. Okay, so therefore different neutrons is obviously going to mess with your mass. Take just a moment and read the example here about the 3 types of hydrogen. You notice that there is one that's way more abundant in nature. Okay, you've got one that's not very abundant at all, and then one that's actually radioactive. So even though they have the same number of protons, they all only have 1 proton, their atomic number is 1, that change in the neutrons is enough to totally change the chemical properties of isotopes. So how do we identify an isotope? It requires knowing both the name and the atomic number of the element and the mass of the isotope. So the mass number is the total number of protons and neutrons that make up the nucleus of an isotope. So the 3 isotopes of hydrogen mentioned earlier, they have a mass number of 1, 2, and 3. They are usually identified by specifying their mass number as shown with hydrogen and helium in the table below. You can see that in your notes, just not on my screen right now. Another example is the uranium isotope that's used for fuel for nuclear power plants. It has a mass number of 235, so that's the total of protons plus neutrons, and it is known as, or can be written as, uranium dash 235. This is called hyphen notation. Again, there's your hyphen. Pretty simple. Isotopes can also be written with nuclear symbols in which the superscript, remember super's above, so this one indicates the mass number, which is your protons and neutrons, and the subscript, remember sub like submarine, below, the subscript indicates the atomic number, or the number of protons. So actually, this has a nice little setup ready for you. If you're trying to figure out the number of neutrons, it's already ready for you. You can just take the mass number, which has both protons and neutrons, subtract out just the protons, and you're left with neutrons. And so I've written this down here, 235 minus 92, and you're left with 143 neutrons. So the one good thing about the nuclear symbol is it's great for the different math that you might need to do on the subatomic particles. And then you also know that there are 92 protons. And since this is not charged, there's no sign out here anywhere, a positive or a negative, then you also know that there have to be 92 electrons. So take a look at our table here. We have the isotope in hyphen notation and in a common name. We've got the atomic number. Remember, it is a capital Z, that's italicized. We have electrons, neutrons, and mass number. Now, just by looking at the periodic table, you should always be able to get the atomic number and the number of electrons. Okay, so for all of these, all of hydrogen has to have one proton. Because it is not charged, it has to have one electron. So all three of your hydrogens both have 1 and 1. If you look at helium, it's got an atomic number of 2. That means 2 protons, which is also what this part is. 2 protons. Because it's not charged, you have to have the negative cancel out. So you've got 2 electrons as well. Okay, if you do not get that to be neutral, your positive has to equal your negative, and your positive is protons, and your negative is electrons. Okay, watch this as many times as you need to until you can get that through your head, or the counting of electrons next is really going to throw you. And then the last thing is the mass number, and so it changed and they gave you the mass number, so then you could just subtract the protons, which was 1, from each mass number to get the number of neutrons. So 2 minus 1 was 1, 3 minus 1 was 2, and then down here, of course, your atomic number was 2, so it was 3 minus 2 is 1, and 4 minus 2 is 2. We'll be getting more practice with that as well, but I really, really want you to get that to be neutral, you've got to have the same number of protons and electrons.